I'd like to introduce Raj Kumar Nagpal. He's a senior manager at Synopsys and serves as co-chair of the MIPI A-PHY working group, chair of the PHY steering group, and chair of the DeFi working group. He has more than 25 years of research and development experience in various fields of electronics, including RF engineering, high-speed serial links, signal integrity, power integrity, and product validation. Raj will talk about today continuing to drive innovation for in-vehicle connectivity for the MIPI A-PHY. Raj, please go ahead and start your presentation. Thank you.
Okay, thanks, James. And okay, so let's start. So today I'm going to talk primarily on A-PHY, and agenda for our talk is here. So I'm going to start with A-PHY 1.0 and then I'll go to 1.1. Then we'll discuss power over A-PHY, A-PHY 2.0 plans development, A-PHY in zonal architectures, and then a modern cockpit display possibilities using A-PHY, and then compliance program and process and where we stand today. So this is the agenda for our today interaction. So let's get to the next slide, please. Okay, so basically A-PHY 1.0 and 1.1, and here is a very uh, brief summary of A-PHY 1.0 and 1.1. So basically A-PHY 1.0 is our first approved spec, MIPI board approved spec, which happened in September 2020. And this is basically allowing, few things which are for the first time in the industry. First of all, this is a long reach, long range, long channel, targeting 15-meter 4-in-line connector channel configuration, directly coupling with the CSI and DSI protocols, which are MIPI protocols. Okay. Uh, Through the protocol adaptation layer, it can connect to display port as well. Okay. And the targeted bit packet error rate of this particular PHY stands for -19. Uh, it is very resilient PHY in terms of EMC noises, which maybe I will cover a little bit. Okay. And it provides both bridge based or endpoint integration, depends, like it will be a phases of integration of A-PHY. It will start with bridge solution and finally it will end up in the direct integration in the sensors itself. Okay. The channels supported are coaxial, which is single-ended. Okay. And shielded differential pair, which is differential. By the way, A-PHY is basically at the top level, it's a full duplex, asymmetric, uh, and power delivery, physical layer. And for the power delivery, I will take you to the specific slide. It has functional safety according to ISO 2626 requirements. And by the way, this specification is adopted by IEEE under 2977-2021. You can actually download this specification directly from IEEE as well. If we take the A-PHY, 1.0 to A-PHY 1.1, the primary changes are that now instead of having it started, supporting Q port configuration wherein dual differential lines are supported. Okay. And that means your effective throughput gets doubled. Okay. It has doubled the uplink data rate. Okay. And then we have introduced some of the modulations in the lower data rate to reduce the effective bandwidth of the channel utilized, and effectively it ends up in the cost of implementation. Okay, so it's a star quad cable support in A-PHY 1.1, enabling lower cost dual lane operation, and effectively it gets to 32 gigabit per second of throughput. So this information we have represented here. So basically A-PHY, in a overall is actually having the gears, okay? Like A-PHY 1.0 and 1.1 are supporting 5 gears. Here it is given. And each gear is supporting, like gear 1 is up to 2 gigabit per second, gear 2 is 4 gigabit per second, gear 3 is 8 gigabit per second, gear 4 is 12, and gear 5 is 16 gigabit per second, okay? And then there are modulation supported. uh, Gear 1 and Gear 2 are NRZ, 8-bit, 10-bit, okay? But optionally support PAM4, okay? So effectively, if you want to use low-cost cable which support lower bandwidth, you can use PAM4 configuration, okay? And then Gear 3 is PAM4, Gear 4 is PAM8, and Gear 5 is PAM16. So you get to modulation bandwidth, which is basically your half, it's basically an Nyquist. And here we are giving you the effective throughput, okay, how much real data you are able to transfer. This is all the downlink configuration. And then the uplink is basically in A-PHY 1.0 and 1.1. The uplink is basically U1 and U2. U2 is in 1.1 and U1 is in 1.0. 1.0 supported 100 Mbps NRZ 8-bit, 10-bit, and U2 supported 200 Mbps PAM4. Effective bandwidth is same because of modulation got doubled, and effectively data rates are here. So this is all about the downlink and uplink data rates, okay? And whatever you see in orange is basically an enhancement happened in A-PHY 1.1. And if you go to STQ cable, like STQ cable is actually dual differential cable, which is here you basically have multiple configurations wherein you can have both lanes in the configured in the dual downlink configuration, wherein effectively you double your throughput because of each line is supporting like 16 gigabit per second. Then you actually are getting 32 gigabit per second throughput between source to sink. Then there's another configuration, which is example 2 here, which is asymmetric configuration, wherein the downlink is 16 gigabit, but uplink is only up to 4 gigabit. And this is, we call it reverse downlink. I'm sorry, I used the downlink uplink word. So it is basically reverse downlink. It's a nomenclature we give it between sink to source, and we in supported data rate will be maximum 4 gigabit per second. And then there is this is, we call it asymmetric configuration. There's another configuration wherein downlink and reverse downlink are supporting same data rates, and we call it symmetric configuration. So these configurations are based on your application requirement, but this is a very brief introduction of A-PHY physical layer, which is 1.0 and 1.1. Okay, let's go to the next slide. So basically, if you look at the A-PHY, complete building blocks, it is PMD, then PCS layer, RTS is a retransmission in A-PHY. Actually, every packet is having a packet message counter, wherein you actually feed in the packet number, and it is CRC protected. And because of any reason, if the packet is lost, my sync can request the source to retransmit that particular packet. Okay, so there is a way to really make it happen. There's a specific state machine, and then after the retransmission there's a link layer. Okay, and above the link layer you have adaptation layer, and adaptation layer can be I mean, say there are many adaptation layers possible, like camera, display port, okay, and then there are other low speed adaptation layer also. So this is the very basic building block of A-PHY system, which is basically depicting here, okay, and then retransmission and narrowband interference cancellation. So basically this PHY receiver has got the ability to really cancel out the interfering noise. Like in an automotive environment, the very basic thing of this physical layer is able to reject the attack noise, okay, which might come because of any system operating in the vehicle. And this is done by basically in the physical layer. This is basically done by a DSP block, which is basically trained to handle the data and reject the noise. So all the filtering characteristics of the A-PHY are really implemented by the DSP block, which is basically using LMS or sign LMS. Okay, there are many algorithms which you use to cancel out the noise, and this NBIC's narrowband interference cancellation is achieved by these mechanisms. Okay, so it's basically more like DSP based noise cancellation, and there is a time within a so there's a packet. Every packet has a overall delay. Okay, uh, the overall delay is 6 microsecond at gear 5. Okay, and within 6 if the packet is delayed more than 6 microsecond, then it will not be transmitted. Okay, so within 6 microsecond, if there is a loss of packet, the request can be generated by the sync to the source, and source will retransmit this packet. Okay, so it's all time bound. And whenever you are sending a packet which was lost, you have a mechanism to really dynamically modulate the modulation from PAM16 to PAM8. Okay, and there is a mechanism wherein you can return back to again PAM16. So there is the constellation is very much dynamic based on the traffic performance. You actually, there's a state machine which plays the constellation of the data. Okay, so by the way, because of these approaches of retransmission and then narrowband interference cancellation, and then uh, you achieve a packet error rate of 10 to the power minus 19. Actually, it is more than a general life of the vehicle. Okay, so this is a very resilient, very reliable trans-receiver link. Okay, overhead because of CRC and other header and footers which go into the packet formation um, are actually not exceeding 10% of the effective data rate. Okay, so this is all. I think maybe you can, if you have any question, you can drop me on the chat. We can take it at that. Okay. So basically, if you really go into the system modeling of A-PHY, so if you really see, this is a system model done in Simulink environment. Okay, and you have to take care of all these are all the noises, okay, which are really possible, which can act, which are attackers. Okay, there are some noises which are static, and there are some noises which are dynamic. Okay, like car noise, crosstalk, echo, POC, power or coaxial, receiver noise. These are all sort of static noises. Echo can be dynamic based on your uplink traffic, but otherwise most of it is static. The dynamic is narrowband interference and BI noise, which is dynamic. So this is the basic, modeling you do, and then this is more, representation of the modeling. If there is you consider there is a traffic and then there is a noise. Okay, whenever NBIC comes, basically whenever there is a noise attack, there is a mechanism to recover the data and cancel the noise, and this mechanism is called just-in-time cancellation. Okay, just-in-time cancellation is a mechanism wherein a known data is transferred from the source to the SIP. Okay, maybe I'll say transmitter to the receiver. Okay, and the receiver is aware, so receiver is using LMS. It knows what is going to be my pattern, and it actually adapts, tunes its FFE DFE tabs to cancel out the noise and recover the data. Okay, so let's say here there is a attack at this point. As soon as the attack comes, you get into a training mode. Okay, when you get into training mode, from whichever PAM you get to PAM2, all training start in PAM2. Okay, you in PAM2 you get the maximum SNR, you detect the noise signature, okay, and then you apply that in FFE DFE tab, and then you start going to higher modulation, higher like PAM4, PAM8 kind of modulation. So this is the mechanism used in AFI to handle the impact and to recover the signal under noisy conditions. Okay. So this is one of the modeling which I did. Uh, and then this tells like you go to, basically you go, generally, you go from lower modulation to higher modulation because you get best performance is lower. You can do better adaptation of your FFE, DFE in the lower constellation, and then you ramp up to others. And then I would say that it is always better to go like this. Now I have shared with you A-PHY 1.0, 1.1, most of the things till the system modeling. And now I am going over to power over A-PHY. So power over A-PHY has evolved, excuse me, over the time. And A-PHY 1.0 and 1.1 have got, PSE and PD, which are defined, but now with the evolution of A-PHY 2.0, we have actually created a separate spec for power over A-PHY. And in this spec, first of all, it is fully downward compatible. Okay, A-PHY 2.0 PO spec respects A-PHY 1.0 and A-PHY 1.1 power over A-PHY specs. Okay, and then what we have done in actually now in A-PHY 2.0, now this is a separate independent specification. It is supporting multiple type of systems, type 1 to type 5, and this is the voltages which are there, which is maybe we have categorized different power levels. Okay, you can really choose your type based on your application requirement. Now it is much broader category, and multiple sensors can be supported using this POA specification. You can see all type 5 starting from 12 to 48 volt. We call it class 1 to class 9. Okay, and then this is my voltage at the power supply equipment, which is this. This is my max min. This is my max current. This is my power. Okay, and this is my delivered voltages minimum at the sink. Okay, or maybe source. It may be either way. And then this is my VP min and max, and this is the minimum power delivered. Okay, so this is all. This is an implementation for the differential, channel wherein you have got PSE and this is PD. There is a definite, structure here. Okay, which is basically first of all isolating a low frequency. Okay, and then of course there will be some coupling to your trans receiver because of because of our delivery, and there is a spec for that, how much ripple can be tolerated with what frequency. Okay, so there's a definite table which, but during design of, if you really see POC in my previous slide was one of the noise, so that noise is coming from here. Okay, this is for differential. Similarly, this is for single-ended, same story. Okay, this is the source and this is the sink. Power source, power driven, and otherwise it is here. Everything I have spoken here. Okay, if you have anything, we can talk later on. So now we go to A-PHY 2.0. Okay, now A-PHY 2.0 evolved, because since working in A-PHY, we learned few things, wherein the evolution has to happen. Okay, and now The industry is moving towards zonal architecture, wherein I will bring some slides on that in the later portion of my presentation. And now concept of software defined vehicle. And software defined vehicle means you have a feature already implemented in your vehicle, and based on the licensing or based on purchase of that feature, you can enable that feature um, in the operation of the vehicle. So this is something like a ATE environment wherein you open up the features based on the costing model. Okay. Then there is some presentation are there which is really depicting the automotive cockpit environment, how A-PHY can be used there. By the way, A-PHY is always backward compatible to A-PHY 1.0 and 1.1. And by the way, evolution of A-PHY is ensuring that all the upper layers are really fully reusable. There is no change, okay? And all the EMC numbers are respected. No deviation on the EMC compliance, either on any of the versions of the A-PHY, okay? So this is all respected. Your environment designed for A-PHY 1.0, 1.1. Above your physical layer is fully utilized. Okay, so you can scaling is always allowed. So this is by design. By spec, we are very careful here to ensure this is respected. So this is A-PHY, a very top level wherein now it is supporting, now you remember in A-PHY 1.1, we said, quad star cable is supporting 32 gigabit per second. But in A-PHY 2.0, this 32 gigabit per second is per lane. Okay. One coaxial line or one differential line supports this data rate. Okay. And it is on the downlink is 32 gigabit per second per lane in A-PHY 2.0. Uplink is enhanced to support 1.6 gigabit per second, and like it is supporting POA as it is always, and maybe it's very clearly written here. 1.6 is brought in to allow Ethernet packet to transfer. Okay, that is one of the reason. And by the way, functional safety and security are very much part of the MAS program where A-PHY is the major component. And my colleague Ariel has already given a complete detailed overview in our first presentation. So by the way, A-PHY 1.1 is already shared with you guys. It is this presentation, this table which depicts gears, data rates, modulations, and then we go to the next. So in A-PHY 2.0, we are adding two additional gears, gear 6 and gear 7. Okay. And gear 6 is PAM8 modulation and gear 7 is PAM16 modulation. You see they are actually overlapping gear 4 and gear 5, but the modulation bandwidth is double. So it is 4 gigabaud and here it is 8 gigabaud. Okay. So that's it. So effectively you are using higher bandwidth, doubling the bandwidth. And this is the data rates. Okay. And it is per lane and this is effective data rate. So this is all on A-PHY 2.0. Okay. But there is a channel change. So I am going to talk about that. So in the uplink, direction, there is another gear added, which is called U3. And this is supporting 1.6 gigabit per second. This is your Nyquist, it is PAM4, so it is 400 megahertz is your baud Nyquist. Okay, so this is all about the uplink. You are supporting U1, U2, and U3. Okay, in A-PHY 2.0. By the way, maybe I have to tell you, whenever you support the higher gear, you have to support the lower gears. Okay, so it is a mandatory requirement from the specification. Okay, now if I go to the channel, okay, so here is a big, by the way, the channel adopted in A-PHY 2.0 is actually having lesser insertion loss compared to the channel adopted in A-PHY 1.0 and 1.1. Okay, compare both for coaxial and differential channel insertion loss are here, and it is basically the same insertion loss is actually, so if phi 2.0 insertion loss is smaller than other channels, and this is a mathematical equation, and coincidentally this channel is very much same as 802.3 cy, and so you can see because A-PHY is having adding gear 6 and gear 7 which are operating at uh, 8 gigabaud, so Nyquist is 4 gigahertz. And you can see at 4 gigahertz, the insertion loss of this channel is closely equal to the insertion loss of these two channels. So in a way, the A-PHY 2.0 channel is becoming less noisy, and whatever additional insertion loss it is bringing in because of higher baud rate, we are actually compensating by its requirement. So in a way, it's very intelligent decision to really hold the things together. And by the way, TXPST limit is minus 922 dBm per hertz. Okay, and gear 6 7 which operate at 8 gigabaud will use TX amp which is 3 dB larger, okay, compared to gear 4 and 5. It is due to the PST requirement. So basically, the amplitude in A-PHY is driven by the PST limits, and that is a criteria, by the way, to raise your amplitude. So you cannot transmit a higher amplitude because you need to meet a PST envelope, and that is a primary, basically it's very sensitive. There's a lot of constraint not to emit more than this much of, spectrum. So in gear 4, so there is another thing which has been brought in A-PHY 2.0 because of some request, wherein we have allowed gear 4 and 5 to be implemented in PAM4 at 8 gigabaud. Okay, so this basically, uh, if you really see A-PHY 1.1 and 1.0, gear 4 and gear 5 were PAM8 and PAM16 at 4 gigabaud. Okay, but some of the companies are more favoring PAM4, and they are okay to really raise the baud rate, and so this is an option provided in A-PHY 2.0 that you can use gear 4 and gear 5 in PAM4, but then anyway you have to raise your baud rate because effective data rate is not changed. Okay, and by the way, this is gear 4.5 using PAM4 at 8 gigabaud over A-PHY 1.1 or 1.0 channel is here. So basically, when you are going for PAM4, you are going to 8 gigabaud, you are coming to Nyquist to 4 gigahertz, where basically your channel is introducing 14 dB of additional insertion loss. Okay, so additional insertion loss is here, and because of this additional insertion loss, the TXPST upper limit PAM4 at 8 gigabaud must still use the same TX amplitude of PAM8 / PAM16 at 4 gigabaud. Since PAM4, PAM2 levels, basically, if you really look at PAM2 level in this slide, I have not put in here. It's basically there's a difference of 2.7 dB, and because of that, you have to basically you have to use in a way. PAM4 provides 14 dB of larger separation between TX levels compared to PAM16. So maybe if you really want more detail, maybe you can use other slides, but here it is not given. There is a, I think there is an amplitude which gets driven by this communication, wherein you basically put a 14 dB of high resolution loss and around 2.7 dB of higher constellation because of differences, and that is deciding the amplitude which you can use in gear 4 and gear 5 at PAM4 modulation. And maybe if you want more detail, I can provide you later on in separate communication. So this is basically A-PHY 2.0 channel. And by the way, This channel is actually based on measurement, and then we added a ENIC and node interconnect structure. And then we model, after adding ENIC and then CPAD, we have this channel insertion loss and channel return loss. Okay, and then this was done in ADS, and this channel is available for anybody who is interested in doing the system modeling of A-PHY 2.0. Okay, so it is already shared. Now, going to A-PHY in zonal architectures, I will just give you a little bit of details. So basically, in a zonal architecture, you have got four zones. Okay, so this is a central computer, and then you have got zone one, zone two, zone three, zone four. Actually, we have focused only two zones to give you better clarity. Okay, and there are some advantages. Always there are some challenges. So I'm just giving you a little bit of overview here. So very big advantage with zonal architecture is that you are reducing wiring harness complexity and weight, because you don't have to carry every wire from every sensor to your central computer. You just have to really terminate your most of your harness in actual zones which are nearby to that sensor, and zone to the central computer you will have less complex harness. And then you know of course, you will use different physical layer from zone to a central computer, and from sensor to your zone, you will use maybe C-PHY or D-PHY. From zone, or maybe you can use E-PHY also. And then from zone to central computer, you will always use E-PHY. Okay. And this is basically the configuration. And then if you really see, most of these red lines are, and sometimes you may come directly from a sensor to your central computer. You don't need to run through your zonal architecture. It depends upon the latency requirements. Okay. And your throughput requirement. You can always choose to be direct. This I will bring in coming slides. And then complexity and weight, you actually improve on your harness, centralized and scalable compute unit. Okay, reduce number of ECUs, because this ECU, maybe a zone is also a smaller ECU, and then it is going to handle a sort of aggregating ECU and handling multiple protocols. Okay, different traffic types. Okay, so this is going to be like that, but it is going to reduce your ECU, local ECUs. And then but its architecture is going to evolve to handle packets from different types. Okay, reduced number of ECU and simpler hardware abstraction, simplified on the air update. Okay, and then upgrade for software defined radio. Software defined radio, I already shared with you the concept. And basically it's going to be a very flexible and very optimized architecture. I'm not calling it simple, but it's well optimized architecture. Okay, and it's very much evolved architecture. So maybe guidelines, aggregation of nodes in space. Okay, proximity by zone ECU, and then central computer, high rate backbone, these red lines. Okay, speed, shared infrastructure across functional domains. Okay, your ECU has to use multiple functional abilities to really work as effective local zone ECU. It will bring in some of the challenges like heterogeneous packets, data traffics. Okay, interoperability, topology, bandwidth, both low and high speed, latency, and sometime efficiency. So these are like, every architecture has a trade-off. So this is basically a big uh, attempt to really give you both features and challenges involved in zonal architecture. And let's go to the next slide. So in a zonal architecture, this is again a simplified version of the previous architecture, wherein sensors, maybe some sensors are low speed or high speed, they can come to a zone. Okay, there are four zones. Some sensors may go directly to the main computing unit. So this is all a different way of representing the previous slide. Of course, benefit is very much, harness gets very much simplified. You don't need to carry everything to your main computer. Okay. Data aggregation happens at the zonal. Okay. No formatting, all packets are intact. Okay. A hybrid connectivity, direct versus via. Okay. You can go direct, but you can go to zone. Data processing centralized. Okay. Maybe I think it is flexible, scalable, software can easily handle it. You can actually make lot of control, lot of observability and lot of controllability possible in this architecture. And it is a very evolving, I think. Okay, so maybe for the A-PHY to support zonal architecture and then evolution of the zonal architecture in an automotive domain, future is majority of high-speed cell links in the vehicle are going to be asymmetric coupling to edge devices. Okay, so this is a top level, uh, futuristic, evolution, how things are going to take the shape and how we at MIPI are really shaping the A-PHY to really fit into the future requirements. Okay, flexible central computer should be able to connect natively both to aggregator or directly to edge devices. Okay, so that sensor or through the zonal architecture, zones are aggregating the traffic. Optimized, standardized communication topology, PHY and protocol should be integrated into the high-speed edge devices. Okay, and backward compatible legacy interface gateways for low bandwidth located in the special area of the zonal aggregator may use 100 Mbps or 1 gigabit Ethernet backbone, which is basically here. Most of these thin lines are that only. This is a control plane communication. All these, blue, yellow, blue lines are thin blue lines are basically control plane. Okay. I think now A-PHY architecture is going to well fit into this architecture because A-PHY is resilient, asymmetric high-speed link supporting 32 gigabit per second per lane with a clear roadmap to further enhance these data rates. Only PHY natively integrating to edge devices supporting CSI and DSI. Okay, and multiplex both the high-speed asymmetric communication and 1 gigabit Ethernet backplane over the uplink over the same cable. Okay, so basically A-PHY is going to really make this whole system possible, as we have really ensured that all the building blocks are part of our A-PHY specification, and this is targeted to really serve the industry in a very positive way. So basically here now I'm going to talk a little bit on the cockpit implementation using A-PHY, a possible. So basically in a evolving, futuristic automotive, we have multiple displays, okay? And then these displays are really becoming, sharing different kind of information. Like now side mirrors are getting replaced with side cameras, and then you have a display. Okay, and then you have a driver instrument display, central information display, a lower control display, co-driver display, and then right side mirror display. So all this is basically coming in the future vehicles, wherein you are going to have multiple displays and you are going to really have all the side mirrors getting out of the vehicles. You see a fuel and you actually are going to really see a better view here. Okay, so and then this is a typical implementation of these displays and their resolution and their sizes. Okay, and maybe I'll give you a little bit more deep, but this is okay. So basically, multiple connectivity schemes including daisy chain. So basically, A-PHY is going to support daisy chain displays, and there's a dedicated slide on the possible implementation. Basically, up to 64 gigabit per second non-compressed data in a single port. Okay, because um, 32 gigabit per second is per lane, and if you use dual lane, uh, you know, implementation, you get to 64 gigabit per second uh, data traffic rate. And maybe if you use Visa DSC compression, you get to 192 gigabit per second. Okay. And this compression is basically a part of possible implementation. You actually save your power because of switching rate. And so this is again depends upon your latency and other quality requirements, but this is one supported. It is supporting a uplink of 1.6 gigabit per second, so your Ethernet traffic can go uplink. By the way, this downlink and uplink are simultaneous data communication. Okay, so in A-PHY, everything is always present. It is not time multiplexed, but it is always present architecture. Okay, you can use, internal, DMS cameras for driver monitoring system. Nowadays, you use camera within the vehicle to see your driver is in, okay, or is he not feeling well. You can really monitor the passengers in the vehicle and really sometime, if it is needed, you can put an alarm or something. This is also important that you are properly awake while driving the vehicle. Okay, so end-to-end functional safety is supported, end-to-end advanced layer security is supported, and then multiple protocols A-PHY is supporting, and which I think Ariel has shown in his slides. And basically, if you really want to really implement a daisy chained, A-PHY architecture, then it is one of the possible implementation is here. This is my central ECU and maybe the traffic generator. You have maybe bridges. Each bridge is basically serving for a different display. You have multiple packets targeted for display addresses, and then you keep on moving and supplying the downlink. This is downlink traffic, and this is uplink. Display can also send an information to ECU, and all the packets are having address to the right display. And this is the way you can implement a daisy chained display system. Okay. And maybe this is a little more deeper view on really giving a real implementation. Okay, so maybe let's try to appreciate it. So I shared with you all these displays and they are given here. And you can see here how an ECU with the, maybe multiple A-PHYs can handle the whole, implementation. Like maybe one PHY is going to your driver instrument display daisy chain to head up display. Okay, another PHY A-PHY is dedicated to your display 1 2 3 in this fashion. Another A-PHY is basically looking for side mirror, rear mirror, and then another side mirror. Okay, and then one A-PHY is basically looking for heads up passenger, uh, display. Okay, for entertainment. And this is the way you can really have. This is one typical implementation using A-PHYs to really handle most of the display requirement. It is just like generic. It is one way of doing it. It's not limiting, but it is just giving an example. Okay, and maybe based on your display 1 2 3, you can have different pixel counts. Okay, and then this will lead to your different bandwidth requirements. Okay, based on your configuration, you may have maybe different pixel density, and you will require different bandwidth requirements. Like this is typical 3 bandwidth requirements shown here. You can use your DSC compression, and then this will lead to this much of bandwidth reduction. Okay, implementation may use dual lane gear 6. So this is our A-PHY gear 1 to gear 7. This is our single lane, and this is our dual lane. And maybe you can see, like, if I want to really connect to 37.6 gigabit per second, I use my dual lane gear 6, and this is 48. I'm providing you a typical example. If you are using compression, you are having your effective data rate is 12.5 gigabit per second. You can easily meet in a single lane of gear 5. Same way you can do everything. This is like If you really need 96.5 gigabit, then you cannot work without compression. You have to go to compression, then you can use dual lane gear 6, okay? And maybe if you are needing 45.8, you can work without compression. You have to use dual lane gear 7, which is 64. So this is one way of implementing. Okay. So now, in fact, A-PHY spec has a very robust compliance program. Okay, which is basically to ensure. By the way, this compliance program is targeted for mass. Okay, and it is starting with A-PHY, but it has to cover all the IPs which are becoming part of ADAS or ADS system. And this is basically we call as mass MIPI automotive SerDes solution. And maybe I'll give you a little bit. So basically, MIPI Alliance is evaluating a compliance plan for A-PHY and MIPI automotive SerDes framework. Okay, so compliance program means you will validate it, and there will be third party validation requirement to get a certification kind of thing. But I'm talking very something which is still under consideration, but I'm giving you where we are. So by the way, we have run a pilot a compliance program in our last face-to-face at Vancouver, and it has been successfully completed. Those who attended this conference are very well aware, and maybe those who are actually member of MIPI are aware what is all the tests shared, data is shared, and this has been a very successful program. Then, by the way, this pilot compliance program was supervised by an independent lab, okay, and there were two vendors, okay, who participated in this compliance program, okay. All aspects of this activity will be reviewed for approval by MIPI Board of Directors, okay. So this is a bigger umbrella, and as we get an approval, we keep moving on this direction, okay. A-PHY tests are defined at a box level. By the way, A-PHY compliance program is at the connector level and not at the internal device level. Actually, the delivery is at the box level, okay. OEMs are going to accept modules which are at the connector level, okay. Of course, silicon will lead to the box implementation, and they will be, internally, company is going to really do that. Anybody, there's no impact on the membership. Anybody want to really get the compliance validation is free, is going can go directly to the labs which are going to support this activity, and this is not going to increase any cost for the members who want the compliance to be done. And by the way, there's a definite flow chart which we have evolved over the time, and this flow chart is going to tell you a little bit on how we are going to implement the compliance program. So A-PHY spec, by the way, here each box is owned by different companies or BP or test labs. So here you can see the color. So this color is MIPI owned. Okay. All this green are MIPI owned. All this blue is test vendors who are like Keysight, Tektronix, or other guys who are really implementing these solutions. There are test labs which are going to really provide you the test services and certification kind of services maybe in future. And there are companies which are basically product vendors. They are going to come into the picture. So I give you a little bit of interconnectivity. So A-PHY specification document and A-PHY CTS are coming from the MIPI work group, and that becomes an input for the MOI implementation, and the MOI is getting generated by companies, okay. And this MOI along with the test setup, this is getting generated by test vendors who are developing the solution around A-PHY, and they might be giving these solutions to test services providing labs, okay. And maybe test labs are providing you a compliance report, and maybe MOI and test setup are basically MOI is getting approved by the MIPI board, MIPI team, core team, which is going to take your MOI, study it. You will actually, the test vendors come with the test equipment and really participate like in a compliance test program, which was a pilot compliance test program. A DUT is provided in solution, a test, they share the results are evaluated, okay, and then we really approve. By the way, this exercise is done only at the pilot compliance level. I'm very careful here that beyond that, it is the board approval and other things, but I'm talking whatever is implemented is at the compliance, pilot compliance level. Then MOI correlation, and then you go back, and if there's a change required in CTS or MOI, you go back. And similarly, if you can participate in interoperability Plugfest, wherein you will come with your solution. Companies will come with their solutions and they will interoperate with each other, and there will be some NDAs. You will say how many you are operating successfully, and there are companies who are going to provide you the DUTs, and this is the evolution of the complete ecosystem, which is self-sustaining. In fact, there's a detailed business case behind it, which I am not really sharing in this slide, but it's well supported with the business case here also. And I think this is one of the demo pilot compliance. This is basically an exercise done at Munich, okay, and then there was another exercise of pilot compliance done at Vancouver. Maybe the members are already aware, there are reports available shared with all the members. Okay. And the program has been very successful, and both the vendors give very close results for the same silicon, and it's a successful event at the Vancouver. And this is all, and it's done. So James, it's over. Thank you very much.
That's great, Raj. Thank you. We've received a number of questions, so
Okay.
luckily we have some time to go through them. First question, Raj, and this is good that you were talking about CTS. This is from Sandeep Menon. Is it possible to explain and give some examples of fault injection and fault detection countermeasures? So I'm not sure if that's something we do as part of the CTS, but this member would like to know about fault injection and detection countermeasures in A-PHY.
Okay. So basically, I can give you my understanding, and it's a good question. Let me appreciate question is very intelligent. Okay. So let's talk of receiver. Let's say you are actually testing your A-PHY receiver, and you want to really detect the performance of A-PHY with a faulty packet and correct packet. So when you say fault injection, your exerciser will basically introduce a faulty A-PHY packet, and you will basically, like, you are giving a good packet and you will give a one faulty packet, and you should see that your bit error rate uh, or your receiver exhibits the failure. Okay, and that is the way you can do a fault injection and validation in the receiver performance. In fact, a receiver uh, will have this test anyway, because compliance will ensure that your receiver is able to detect a faulty packet. By the way, fault you can introduce by faulty CRC. Okay, generally, receiver is basically going to receive the packet, recondition the packet, extract the data, validate the CRC of the packet is expected. If the CRC is failure, so there is a packet failure. So fault injection means your file receiver should indicate a fault, uh, faulty packet, and should actually request the retransmission of that packet in a way based on your ability of your exerciser. If it is supporting the retransmission state machine, then you can validate the closed loop operation of your receiver. So I hope this is primarily fault injection and fault detection is more towards the receiver. From the transmitter side, if you really want to validate transmitter for the fault injection, your um, A-PHY exerciser will basically generate a wrong packet at the data link layer or protocol adaptation layer, wherein you can set faulty packet by CRC, and then you will send it through the transmitter, and then when transmitter is regenerating the packet, it will it has to meet some of the what do I say, scrambling requirements. So by the way, transmitter is having a scrambler. Okay, so scrambler will scramble the pattern, but fault detection at the transmitter. Maybe I am not very clear on the transmitter side how you can do it. Probably at the receiver, I have already told you how to do it. For the
Okay,
transmitter, I
Raj.
will come back how to do it.
There's a related question. This is from Bob Chila. For the packet error rate of 10 to the minus 19 to achieve that, is that achieved without error correction codes? The first slide was about CRC in many different places, but error
Mhm.
correction codes were not mentioned. So the question really is, how is that 10 to the minus 19 achieved? Without ECC or with
No, no, no.
CRC, or how is that achieved?
So by the way, A-PHY supports a retransmission. So error correction is by retransmission. So whenever there's a wrong packet received, you have a time window within which you can, the sync can request, maybe receiver can request the transmitter, or maybe sync can request the source to retransmit this packet. So this stands for minus 19 is with the RTS taken into account, not without RTS. So error correction is through the retransmission. I
Great,
hope I replied. So basically, this stands for minus 19 packet error rate is calculated when the PHY is supporting the retransmission.
correct. But in addition to that, Raj, I think each of the A5 frames also have their own CRC protection, correct?
Correct, correct. And by the way, if you talk without RTC, what is my packet error rate? Then it is not 10 to the power minus 19. Then it is different. It is lower. But in a real system, RTS is very much part of the physical layer. Like when we do the system modeling, if I'm not doing RTS, I use lesser packet error rate requirement. When I use RTS in my system modeling, then I raise my packet error rate requirements. So, so I hope I have explained your question. So you
Yeah,
have to use RTS to get test for minus 9.
Bob indicates thank you. Another question. This is from Michael McDonald. On the implementation side, can you give a sense of the size and power and the different power at different data rates and any special needs required for the PHY and packaging? So he's talking about implementation size, power, different rates, and special needs for the packaging and the PHY.
Okay, so I try to reply. The question is very deep, and nobody will give you the power here in this presentation. It's very much confidential. Okay, but take my point. Generally, the files which are supporting noise cancellation are using DSP. Okay, so the objective of this file is um, performance, not just power. So maybe this file is more governed by the resilience to handle the EMC and what kind of packet error rate it can offer than to really be that what is my minimum power in here. So there's a different perspective. Number one, here the perspective is performance and under EMC noise conditions. And power wise and power and area really I will be not able to give you here in the call. Maybe if you are really interested under some NDA, you can request the companies who are implementing it. That's all I can say. But maybe if you really want to get a very rough figure, maybe then you know the data rate, you know the channel, and you know the amplitude, then one can calculate theoretically also. Maybe amplitude wise, like it is 250 millivolt at the transmitter power. If I talk of transmitter, then the power will be driven by 250 millivolt. Then you know your baud rate, okay, and then you know your channel and termination. Termination, if it is single-ended, it is 50 ohm. If it is differential, it is 100 ohm. Then you can get a theoretical number, mathematical, that we can do always. But if you, but otherwise, exact implementation, PPA, I don't have.
Great. Okay, I've received this question in the back channel by email to me. This is regarding A-PHY 2.0, Raj. The question is, what are the planned enhancements for A-PHY 2.0 and how has power over A-PHY 2.0 advanced?
Okay, good question. So basically, I need to take you to a slide, then it will be better.
And for everybody, while Raj is navigating to that answer slide, if you have any other questions, please type them into the chat and we can address them. If not, we will wrap up this session a bit early and restart at 9:45, which is when I believe we start for the next session. I'll double check, but I think it's 9:45. So please type in your questions in the Q&A chat. And if we get no questions, then we'll wrap it up early. Go ahead, Raj.
Okay, so by the way, A-PHY 2.0 is basically adding two additional gears, okay, gear 6 and 7, in PAM 8 and PAM 16 modulation, okay. It is 8 gigabaud is my baud rate, okay. And this is one major enhancement in A-PHY 2.0 in the high-speed domain, which is generally downlink, okay. And then additional, another update is supporting higher uplink data rate, which is basically 1.6 gigabit. This is two changes. And then the third major change is basically now we are having power over A-PHY, which is basically a separate specification. We have got 5 classes or 5 types, sorry, classes here, and then type 5. So basically, A-PHY, with the evolution of A-PHY 2.0, by the way, POA has become a separate specification. And now this separate specification indicates supporting 5 power types, okay, which is type 1 to type 5. And based on your source and sink requirement, you can choose any of these, okay. So this is a very top level. And then basically there is another thing is that another thing is the channel has changed. Channel in A-PHY 2.0 has changed, and this is a new channel. These are the old channels. So this is a very top level. If somebody asks me, what is A-PHY 2.0 over A-PHY 1.1 or 1.0, this is my reply.
Okay, thanks, Raj. Are there any other questions, comments, or concerns that people would like to put into the Q&A session? We'll just give, say, another minute because we do have a few more minutes. And I'm just checking also my listed of email questions. I think, Raj, you have addressed them all. Let me just quickly check. I think that's everything. We talked about the packet error rate. Yeah, looks good.
Yeah. I think we discussed everything.
I think so too. Raj, thanks very much. That was great. Thank you.
Thank you, James. Thank you very much.